Hello, y'all. How y'all doing? Hopefully my sound is okay. Need to change this moment here. Hearing myself, not sure why. Let's see here. Oh, so this. All right, there we go. Nope, that didn't fix it. It, I think so. Nope. All right. You're putting nope, it still didn't do it. So I'm not sure where my volume is coming from. Testing. Testing. My one of my settings changed automatically. I'm not sure why that happens sometimes. There we go. Should be working now. So awesome. Excuse me for being late. Hopefully everybody's doing well. Looks like we did get one input of a topic to discuss. Gently's mentioned wanting to discuss probabilities. Gently said non-zero probabilities. Can a probability be pure mathematics, abstraction only, or are probabilities based in physics? Is non-zero probability just mathematics inside non-physical infinities? So ironically, I've been dealing with probabilities a lot. I'll let y'all know that I'm taking a thermodynamics class right now. Thermodynamics deals a lot to do with probabilities. So I don't think probabilities are necessarily uh, germane to one type of topic or system. It's just that probabilities are a certain aspect of nature, that certain things are more likely to happen based upon the accessibility that state has. So um, if it's in the middle of a sunny day, it's more likely to be warm, for instance. So it's more probable that you'll go outside and feel warm in the middle of a sunny day. Now, of course, if it's wintertime, that might change a bit. But generally, if it's very sunny outside, it's more likely that you'll be warm. In any case, you'll be warmer than if it's not sunny. So I don't think necessarily, in my experience, that probabilities are put into one side. Now, I did take a class in probabilities. The class was called, I think it was even called probabilities. Let me take a look and see. probability 1. So M362K, probability 1. That was actually the name of the class. It ended up being, of course, mainly probabilities, but there's so much math stuff in that class that we had to do that it seems like it should have some kind of supplemental name like probabilities and the statistics and what do you call it, combinatorics. We just did a whole lot of counting and probabilities and things like that. But it was cool. I enjoyed the class. So definitely run into what I learned in that class. And so right now I'm taking, as I said, thermodynamics and statistical mechanics. And so we're dealing with a lot of probabilities. But before that, as a prerequisite to this class, I had to take modern physics. You heard me talk about that class before, but that class was a sort of survey class where 1/3 of it was quantum physics, 1/3 of it was uh, thermodynamics and statistical mechanics, and 1/3 of it was relativity. So in both of those classes, I was able to see more how statistics refers to physics and see the applications of statistics and physics. But still, it didn't in any way sort of end up being like like you saying, like pure mathematics. So my understanding is that mathematics, the best way I've heard it said, I don't remember who this quote is attributed to, but that mathematics is the language of physics. So one of the reasons why physics is valid as a science is because the physics works to mathematical precision. So when you uh, put gas in your car, you probably don't go to the same gas station every time, and even if you do, you have to refill the tank. The tank at the gas station that you get your gas from. But we find that we don't have these wide ranges of results. It's not like you pump your gas on Tuesday and the car is revving, and you pump it another day and it's false starting all the time. It runs pretty consistently. And that's because the processes by which we make gasoline is done to a very scientific and mathematically precise way. So same thing with talking about statistical mechanics, building a refrigerator. Those things are based upon thermodynamic principles. Refrigerator is basically a heat engine. So, you know, you don't normally go to get a refrigerator and it works all kind of varied ways if it's working properly. I mean, of course, a certain percentage of manufactured things will have a malfunction to it or a defect. But if it's working properly, generally, if you buy the same exact make and model of refrigerator, you can buy 100 of them and they'll work the same way. They'll cool to the same temperature in the freezer if you put the setting on the same. So all of these things are made to mathematical precision. So uh, as a budding physicist and astronomer, I find it an error to suggest that probability can be solely mathematical. It's simply that probabilities are one of the ways that we recognize nature to work. And then an example that comes to mind, by the way, I was about to say that y'all would have heard me say, but I was actually speaking about this on my STEM channel um, about Brownian motion. I believe talked about it a bit. So I'm a learning assistant for the Modern Lab, which is the laboratory for the class I was just mentioning, that survey class where you do thermodynamics and relativity and quantum. There's a laboratory where you do experiments to get some hands-on, first-hand experience with these things. So this is the same class where I measure the speed of light. This is the same class where I observe the relativistic effects of an electron. This is the same class where I measured the energy of a scattering electron and was able to see how it could break, and how we could take that electron and break it into mass per E equals mc squared, and depending on what angle you observe it from, it you could either see it split into two gamma rays at about what 205, 206 milli electron volts, or you could see it break into three, and so on and so forth. And another experiment that I didn't do myself, but that some of the people in the class are doing, is called Brownian motion. And the idea is that if you have a uh, a container of gas, or even just a liquid that you, let's say, drop some dye in, the particles in that gas or in that liquid, if you have enough of them, will move in a very probabilistic way. They call it in mathematics a coin, either a coin flip or a random walk basically. So it's like this particle is vibrating, it's bouncing against all the other molecules in the liquid or all the other molecules in the air, and randomly is going to go in some direction. It's not going to just bounce back and forth in the same place. One molecule is going to move out the way, and it'll move a little farther that way, and so on and so forth. And basically, you can probabilistically determine how far a particle is going to move, and it's very, very consistent. And just says acoustic. Please be more specific. Am I having an audio issue? I need to turn it down some. So, to be more specific, just Mari, what was wrong with the audio? I'll try to fix it. So give me one moment here. Let's see what the audio issue is. So just Mari said acoustic, please. Okay, awesome, Lisa. Hey, what's going on? All right, well, I'll turn it back up. Let me know. Be more specific, just Mari, if there's an audio issue. And what was I? Oh, yes. Yeah, doing good. Doing good. So, getting accepted into some colleges for grad school. I'm definitely going to grad school. Now it's a matter of which one I'm gonna go to. I have an idea which one. I'll let y'all know when I finally pick one and decide upon that one. But I have a good idea what it's gonna be. So give me no more than a month. Probably about March. I'll lock down and decide so I can start focusing. It's a lot of time on the grad school. I'll be visiting my second one in March, which is the one I really think I'm going to go to. Classes are tough. Of course, it's upper level classes, 5 of them, so it's to be expected. But overall, it's a good time. So, what I enjoy doing in the end. But yes, and Lisa says, "Boom, congrats." Nah, I didn't even apply to those. Yeah. So I know my limits, and plus, I wouldn't even want to go to, like, it's iffy with the Ivy League schools now. The word is woke. I don't really like that word in that context anymore. But they've gotten so gender ideology and critical race theory out, and I don't even want to go to a school like that. Any school that in any way indicated to me that they were woked out, I just didn't apply to. Even if I was in the middle of applying and something on the application let me know, I just didn't go. Well, actually, Lisa, as a physics uh, graduate student, because we're in such demand, I guess, uh, I'm gonna get paid to go to school. I'm gonna get paid to go to grad school. I will have to work, so I'll be a teaching assistant in class. So, for instance, I may lead discussion sessions and grade some papers. Eventually, I may teach a class of my own. But my tuition is going to be paid. My medical bills are going to be paid, like my medical, what do you call it, insurance. So yeah, I won't have to pay to go to grad school. Yeah, so that's generally the case for physics because it's hard as hell. Physics. So physics, astronomy, I don't know about engineering, but definitely physics and astronomy. So yeah, I'm going to get paid. It's just a matter of how much I'm going to get paid. So that's one of the things I'm looking at. I'm looking at the schools that I've been accepted to, and some of them are putting me up for a fellowship, and some of them have their default base amount that they pay. But either way I go, whichever school I go to, I'll be getting paid. It's just a matter of how much. But of course, I have to perform. Like, you can't go there and like fail or something. I gotta go there. I gotta earn at least a B and everything. If there's enough funding, then I don't have to teach, but I actually enjoy it. So, I mean, I'm fine with that anyway. But for the most part, I'll be spending half of my time in class, half of my time helping in the classroom, teaching. And then after 2 or 3 years of doing that, then you become a full-time researcher, and then you do between 3 to 5 years of research, and then you for your PhD. Um, you know, what do you call it? Dissertation and presentation. So, but for all that process, as long as you're doing well, you don't pay for graduate school for a physics degree. You just have to work your ass off to get there. Is all it is, or just be good. I mean, I think I'm a mixture. And trying to like halfway work my ass off, and half, I mean, I'm a little bit good. So it's right to say I'm getting a few offers, so I'll be all right. The brownie in motion. Yeah. So that experiment is pretty cool. So basically, I don't know the details. So like I said, I didn't do it. I'm not really interested in brownie in motion too much. So I can't even say I really read it a lot. I mean, I had to learn about it in my modern physics class because, again, it's the lab for the class. So I had to read about it and learn about it. I'm sure I took a few test questions on it, but it's not really interesting to me, so I didn't pay too much attention to it. But suffice it to say, we can predict or probabilistically determine how far a particle is going to move generally, and it's pretty consistent. So um, the universe is highly probabilistic. That's actually what thermodynamics is one of the cores of thermodynamics. As I'm actually in the thermodynamics class now, I'm really learning it from an expert. My professor is really good. He really takes the time to go through concepts and explain things, and so now I'm actually learning the real ins and outs of thermodynamics. And one of the foundations of thermodynamics is that it's based upon systems of large amounts of particles. And he actually addressed that in class just the other day. So basically, if you have a system with just 10 particles, that's not something that you'll really do thermodynamics on, because you could just count the configurations of the system manually, you know. But if you're dealing with something that has, let's say, 10 to the 23 particles, so 10 to the 23 is Avogadro's number. So basically, if you look at let me bring up the periodic table here. And this is basically the periodic table that got me through chemistry. Uh, and it may seem strange that a physicist has to take chemistry, but when you get to quantum mechanics, and even, you know, some higher level physics class, you understand why you have to take chemistry. It's definitely not just a superfluous class. Um, but there's this periodic table that I really like, that I've used a lot. So give me a moment. Let me go to my share screen. And I'll get that shown so we can look at this a bit. Oh yeah, definitely. It's all right. Definitely. So as I continue to progress, more and more things are overlap. Like for instance, in my cosmology class, we've been talking a lot about relativity, because cosmology is about the universe at large, the big things, big distances. So invariably, when you're talking about something very far away, you're going to have to talk about relativity if you're going to talk about it above a certain level of accuracy or precision. So in my relativity class, we talk about cosmology, because that's one of the ways to specifically apply relativity. You know, so it's amazing. And like I said, in my thermodynamics, we're talking about chemistry. In my quantum, we're talking about chemistry. My professor was showing us was teaching us the quantum mechanical basis of a chemical bond. So, but I'll get into that. Let me not lose my periodic table point, and I'll tell y'all an interesting thing about bonds of atoms. So I'll hit this show. All right, here we go. And let me move this over a little bit so I can see it a little better. Oh, I didn't even change my whatchamacallit thing. Look at this. So looking at this periodic table, when we look at the atoms here. So why don't we pick hydrogen, since that's an important one in quantum mechanics, because that's the pretty much the only one we can really fully explain to a great degree. But you can see how it says 1.08, 1.008, that's the solar mass. So the idea is that if you have a mole of hydrogen, that mole will weigh 1.008 grams. And the mole is 10 times 10 to the 26 hydrogen's unique atoms. Or if you have, like, for instance, oxygen, right there, 15.999 or just 16. If you have a mole of those things, then you'll have about 16 grams of oxygen. And that's how these things are designed. So when you get into quantum mechanics and when you get into physics, like thermodynamics, you talk a lot about moles of things, because it's when you get a lot of a particle, when you get a bulk amount of things, that's when you start getting these probabilistic effects. And you get numbers that are so big that we end up starting to use approximations like this thing called the Stirling approximation, where you basically use logarithms to convert these large numbers into something that's easier to work with. And then later you can convert them back if you need them in a bigger form. And like I had mentioned before, a refrigerator, and calculate the heat engine, the things that needs to happen to make that work, right? Oh yeah, certainly. I can put the link to this page. One moment here. Let me get to the original. Uh, uh, there we go. So this is the default page here. So I just think it's a cool table. So I refer to it a lot when I was in chemistry. And, partly because I nice colors there. And that's pretty cool. And I forgot my other side question. I was going to talk about some kind of side thing. What was it? Oh yeah, all things are related. And chemical bonds. That's right. So the way it works is, and I'll go ahead and write this down. Let me bring up my Discord here, and we'll get some Discording going. Sure again. Close on me. I actually have to do this homework bit. I've been working on it for hours earlier. Finally, I think I'll be able to do it. Thankfully, the professor gave us an extension. I'm pretty sure a lot of people asked for one as well. So the idea is, let me remove the scrolling text since it's incorrect. So, I can actually increase this now. Let me actually increase the size of this as well. All right. So the idea is that, okay, so we have quantum numbers, right? And this still relates to probability as well. The topic that Gently's brought up, but basically you have certain energetic states that are more probable. So basically, looking at it like we have n numbers or quantum numbers for subatomic particles. So let's say an electron is in certain orbitals, and each of these orbitals, the way it works is the n number is basically the primary quantum number. So you can have an electron in the at the n level, at the 1 level, the 0 level, and so on and so forth. So to use the one that I did earlier, let's say that n equals 2. Subatomic particles actually have angular momentum to them. So if you look at an electron, it's negatively charged, but if you put the electron in an atom like a hydrogen atom, the hydrogen atom has a charge. I mean, the proton has a charge. So what's going on is you end up having two particles with magnetic moments, and they interact with each other, and it causes what's called fine these fine adjustments to the levels of atoms. So let's say we have n equals 2. I believe the L is called the angular orbital momentum. Is going to basically, the numbers it can have is 0 up to uh, n minus 1. So if n equals 2, I can have L equals 0 and L equal 1. And if you're dealing with an electron, like we're talking about the hydrogen atom, the atom has spin, right? We may have heard the term spin before. It's not that the particle is actually spinning, it's just that it has an inherent property in it that we can determine is either pointing, let's say, up or down, right? It has this inherent property that's going one way or the other, and so we call it spin. So this would be called S or ms. I'll just call it S for spin 1/2, and the spin will combine with L to get another quantum number, which will basically gives us the levels that the electron can fit in. So basically, the J quantum number is L plus or minus S. So it has to be greater than 0. So the L level will have J equals 1/2 because you just have the spin you can add to it. The L equals 1 will have J equals 1/2 as well as 3/2. So what happens is each of these ends up being levels that the electron can fit into within the n orbital. Right? So you'll end up having an n orbital. Let's say this is the n orbital, but this will split into a 1/2 here, a 1/2 here, and a 3/2 here, related to the L equals 1, L equals 1, L equals 0, all in the n equals 2 level. And what happens is when you have, let's say, two hydrogen atoms and an oxygen atom, they end up sharing an electron because there's a lower energy state where, and I may be circling the wrong one, I'm just saying, one of these is a lower energy state where that hydrogen atom can, in a sense, share an electron with the oxygen, and basically it fits into one of these subcategories of energy, and it's the lowest level of energy. It's lower than here, and what wants to happen is the electron wants to get into the lower state possible because it's more secure. This is why things are not just flying apart all the time, because when things bond, they're in a lower energy state, so they're secure. Just like how we were to have, let's say, a well, or a like a roller coaster where there's a little downward thing. If you drop a ball, it's going to go like this, but then it's going to settle at the bottom in the middle because it's the lowest energy. So things want to find the lowest level of energy because it's more secure. So basically, this quantum effect of having these different J levels is behind atomic bonds. And when you look into them in detail, you can actually find the lowest energy and see why, for instance, you know, H2O is what it is, because it's just the way the energies align that they bond. So all that to say that when you talk about chemistry, right, when you talk about bonds of things, it's actually quantum mechanical. But we didn't really talk about it that way in chemistry. We just talked about it from bonds, and you could talk about it that way, and look at your bonds, and you could draw it out, and you could just draw an electron being shared, and with a strong bond you might draw 3 lines if you're illustrating it, and so on and so forth. But behind that, there's a quantum mechanical reality, a very consistent quantum mechanical reality, where we can calculate the precise energies that allows for certain elements to bond and certain elements not so much to bond. So it's pretty interesting. So all of these things, relating it back to probability, is how we can do these things, because all these things are mathematical. I mean, even to look at it, we talking about atomic particles, but we listen to these things as numbers, and we have you know mathematical properties that determine these numbers that, that are confirmed with experiment. And of course, once we observe these things through experiment and we start to model these things, and then we start to predict things that we haven't seen yet. We start to predict, well, what'll happen if I put these two molecules together or put these two atoms together that we haven't seen in nature yet, let's say. So we don't know what's going to happen, but we could model what's going to happen and calculate what's going to happen. But what we understand from what we have seen. And then if our predictions comes true, if we put those things together and the bond happens that how we expect it to happen and the amount of energy is released or absorbed, how we calculate and so on and so forth, then we know that our understanding is sound. And eventually we start to do various things with the technology that we have and make new materials like we're doing today and things like that. So a good topic, probability. Uh, uh, I actually enjoyed that class. I enjoyed the professor. Ironically, we was talking about how grad students teach classes. She was a grad student, actually, a PhD student. In her later years of, usually you don't teach the class yourself until you're in your later years of being a grad student. But she actually held a really good class. So I look forward to either when I have my own class or at least uh, um, as a teacher on record, which you are, you teach your own class if you're the teacher on record, but technically you're not the professor. So what else we have? What other things y'all might want to talk about? I'll keep the Discord up. And be sure to drop a line. I see there's some people dropping in. Make sure to drop a line. Let me know you're here. Let me know if you have any questions or comments. Oh, maybe Just Murray was asking to let acoustic be a topic. Is that what Just Murray was saying? I don't know. Just Murray popped out. I haven't seen Just Murray again, so I'm not sure if Just Murray was saying the acoustics in my audio something was wrong with it, or he wanted to discuss the acoustic topic. But if you're still there, let me know. I'll do the best that I can on that. It's awesome. So why don't we do a little bit of probabilities or something? So let's say an interesting thing we learned about in quantum in thermodynamics that I wasn't aware of before is something called an Einstein particle. So the idea is that um, Einstein, it's amazing how much stuff this guy figured out and how many things in so many subjects. As you start to get into higher levels of physics and astronomy, uh, so many things this guy figured out, and so many things are named after him is amazing. Um, like right now, we talking about him in relativity, of course, and we talked about him in uh, uh, thermodynamics. Talking about him in cosmology as well. Yes, thermodynamics. So what's going on is basically he discovered, or I guess you could say, decided to model a particle like a physical object as a series of oscillators. So if you imagine, let's say you have a carbon atom, right? Let's say this is a carbon atom, and we talked earlier about Brownian motion. Well, basically, this carbon atom can vibrate, and it can vibrate in three different ways. So let's say it can vibrate in the x dimension, it can vibrate in the z dimension, and it can vibrate in the y dimension. So it can vibrate in three different dimensions. And each of these directions we can consider it to be an oscillator. So basically the way it works is it doesn't seem like it'll be this way, but it is that there's a concept in classical dynamics predominantly, and in waves even more so, called the simple harmonic oscillator, where if you have a potential or if you have any kind of a will, like let's say you have a spring even, right? Where the spring has a certain tension on it, and as you pull it, it'll pull back As long as you're within the small range where you don't break the spring, it's going to go back and forth in a very, very, very predictable way, right? And we could calculate the period and the frequency and the amplitude, all of that stuff very accurately. Well, since we know matter is not breaking apart, as I was saying earlier, Einstein decided, oh, what if we model matter as a bunch of oscillators that are oscillating in three different dimensions? And we call this an Einstein particle because you could actually treat matter like that. So basically, we look at these things and we can calculate the energy thermodynamically with a particle by using a simple formula. So basically, this formula is n plus q minus 1 over q. So what this means is that, let's say we have an Einstein solid, or basically any system where you have an amount of energy. So for instance, looking at this Einstein solid, there's a certain amount of energy that's causing this particle to go back and forth. And you have so many particles that the energy is vibrating amongst, right? So if you have a particle here and a particle there, they might bump into each other, and maybe one will transfer some energy to another one. But still, there's so many particles and so many ways that energy can bounce around. So we can imagine that by saying that this particle, let's say we have so much energy. So let's say these circles are energies, and let's say we have two particles. So this would be our number here. So if you wanted to, let's say, calculate how many different ways um, energy can be divided amongst the system, you might, for instance, call the energy Q, and then call the total things N, and I'll check and make sure I'm picking the numbers properly. This would be, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be like 9 plus 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 1 over 8. And this configuration is a particular, I was speaking about probability. This is actually a probabilistic way of writing this, where what you're really doing is using factorials and saying 9 plus 8 minus 1 factorial over 8 factorial over 9 plus 8, at least uh 9 minus 1 factorial. And this will give you the amount of ways that energy can be maneuvered around the system. And Lisa says this is just a conceptual framework to calculate the energy of an atom. Not that it's truly vibrating like that in reality. I just want to be sure I'm following. Yes, it is vibrating like that. Turns out that it is. Turns out that it is vibrating like that. So let me actually pull up that. Actually, let me pull up the textbook, and we could look at that. So it actually turns out to be quite accurate. It's amazing the stuff that Einstein was right about. Even the stuff he was wrong about, he was right about. We could talk about that. But he was definitely right about this. Let me bring up my thermodynamics book. Move it again. All right. So let me search for it. Einstein solid. And this book is called An Introduction to Thermal Physics. Good book so far. Gets it done. All right. So here we go. Examples of quantum oscillators include the vibrational motion of diatomic and polyatomic gas molecules. Let me make this a bit bigger for you. But an even more common example is the oscillation of atoms in a solid. In a three-dimensional solid, each atom can oscillate in three independent directions. So if there are n oscillators, there are only n over 3 atoms. The model of a solid as a collection of identical oscillators with quantized energy units was first proposed by Albert Einstein in 1907. So I refer to this system as an Einstein solid. So this is actually, I mean, this is the way it works. We literally have particles that are vibrating in one of three different axes or all three axes, and it can be calculated in this way. So these things are not, and this is the formula I was writing down there. You can see that's the Q plus n minus 1 Q, and you can see I wrote it down with numbers, but this is a probabilistic way of counting up all the different ways that these particles can be configured. And it looks like I did have the counts a bit wrong. So it looks like n is the number of oscillators. So in my example, n would be 2, and Q is the number of energy units. So Q in my case would be 8. So basically, one of the ways we know that it works this way is because we can calculate the energy of things. Go ahead, Nara. What's your suggestion? Let me put the chat back on the board here so people can see the chat that's going on. While Siddharth is putting his suggestion out. And Siddharth says, I think you should cover special relativity from scratch. And Siddharth says, I think you should cover special relativity from scratch. And Siddharth says, like make a series talking people from Galilean to Lorentz transformations and so on. I really think it's one of those brain warping ideas. That way folks just aren't familiar with it. Thanks. Okay. Could do that. Next week I can start doing some relativity stuff. So sounds good. Yeah, thanks for the suggestion. I appreciate that. So next week we could look for that. I'm still working on. Did I open up the wrong thing? I might have opened up the wrong thing to try to get the chat for y'all to see. But it's not such a big deal for me, y'all in chat. But just in case, if it don't take a moment, I'll go ahead and put that up. But yeah, you could do that. But I'll finish with some thermodynamics today, and we'll talk about some relativity next week. Keep in mind, I'm not a pro. We'll be going like from the beginning next week. But it seems like that's what you mean as well. So relativity is actually a pretty heavy topic. There we go. That's what I needed. Boom. Boom. There we go. Now y'all be able to see the chat. Awesome. We'll do that. So I'll make a note to myself. Relativity next week. We'll start from the beginning with some Galilean transformations and all of that, which I have to refresh myself up on. We actually did that a little bit at the beginning of this class, but he didn't actually make us do the Galilean transformations. He just went through them. Ironically, I did more Galilean transformations in electrodynamics because we had to do that for relativity. Awesome. Sounds good. I'll do that in there. So yes, these particles, we actually calculate the oscillations and energies of particles like this. I'll do that. I guess so. Yeah, I can say Newtonian is definitely more known, which I like. I actually really like Newtonian. And I was in my, me and my friend were doing our homework for thermodynamics. Hey, what's going on, Sean? Good to see you. And he's taking classical now. and I was able to help him with one of the problems from memory. So yeah, classical definitely makes sense. I like it. But relativity and stuff is fun too. So, but yes. So, and eventually, what we're starting to get to now, by the way, is these Einstein particles. Like here, you can actually calculate the energies and the entropies of these objects when you put them in contact. It's ironic because if you have two different systems and you put them in contact with each other, the entropy of the combined system is the entropy of both systems multiplied. It's quite interesting. So basically, we have, if I remember the formula, S equals ln this. And I think I'm missing a constant. But I should just say I think that should be sufficient. So basically, like there's a constant here, but I don't remember what that constant is. But we'll just focus on the main part of it. So basically, entropy, one way of looking at it is it's the logarithm of the multiplicity of a system. And the idea is that the system, the configuration that has the most entropy will be the configuration where you're in the most likely macro state, like the macro state that has the most micro states, like the most likely to happen. And if you have two systems and you put them together, basically you have the so let's say for instance I have a coin and I can flip that coin, and get heads or tails. So that's going to give me two different options. But if I flip two coins, the second coin is also going to give me two options. So when I flip those two coins together, I end up with four different options I can get, right? With one coin, I could get either heads or tails. With two coins, I could get heads on one and heads on the other, or I can get heads on one, tails on the other, or I can get tails on the first, heads on the other, or tails on the first and tails on the other. So I get four different ways. So each time we add another particle, it multiplies. So the multiplicity of two different systems is the multiplicity multiplied. So it ends up being S of the S total equals ln of the two multiplicities multiplied. But when you use the principles of logarithm, you end up with log of one plus log of the other, which means it's S of one plus S of other because, again, the entropy is the log of one system. So I'm going to call this A and B. This will be log A and log B. So the entropy of A plus the entropy of B ends up being the entropy of the total system. And this image that you see here in the book is starting to touch upon that about when you put two systems together. So going back to Lisa's question and point, yes, we very much calculate the energies of systems by modeling particles like atoms and particles, for instance, as oscillators in three different dimensions. And it works quite well to get the energies that we need to do things quantum mechanically. I mean, not quantum mechanically, thermodynamically. Lisa says, if you're writing something, we can't see it. Oh, no, I wasn't writing anything. I was just pointing in the book. Oh, I was. I'm sorry. I forgot myself. I was right. So, oh my gosh. I guess I was out. I have it right. Let me put both of these up. I started focusing on one or the other. Let me get both of these up. Pull up here. So let me share and I'll reiterate that because it's actually worth going over again. So I have my whole thing together, shrink them down a bit, and there we go. So now y'all can see both of them at the same time. So the idea is to reiterate and make sure we're clear on it as well. So, in matter of fact, I'll just write it more clearly because I guess in my mind I was kind of writing it mostly to like explain it to myself at the same time a bit. Let me make sure I write it so y'all can understand it. And actually, let me find out what that constant is anyway while I'm thinking about it. I don't remember what the other constant is, but there's another constant to the entropy equation. I showed it to y'all the other week, but I don't remember what it is myself. It's ln pass it. Only thing about this book, like they gave us the book for free in the class, which is good. You don't have to pay for the book. The only bad thing is the table of contents doesn't work like normal, so it's a bit harder to find stuff. But it is a free book, so can't beat that. Oh, here it is right here. Okay, well, it's just K. Oh my gosh. So, all right, so entropy is S equals K, the Boltzmann constant, times the log of the multiplicity. And again, the multiplicity is the different ways that a system can manifest itself, right? The different configurations, all the different configurations a system can have. That's the multiplicity. And Nair says, got ahead. Also drop an email later with some stuff I might help you do. Sounds good, man. I'll look for that email. Oh yeah, got it worked out, Lisa. So this is the entropy equation, and this omega is the multiplicity. So if I have a system that can be configured in 100 ways, then this number will be 100. Just like if I have a coin, let's say if I have 6 coins, right? Each of these coins can be flipped and get heads or tails. So now that's going to multiply to 2 to the 6. So basically, a configuration or a system with 6 coins will have 2 to the 6 configurations you can have. You know, this one can be heads while all of these are tails. And then this one can be heads while all of those are tails. And then, you know, this one can be heads and heads while all of those are tails. And when you count all the different ways, the multiplicity will be 2 to the 6. So the entropy of that system will be S equals K log of 2 to the 6. And this will give us the entropy of that system. Right? But if I have another system, let's say I have a second system of 6 coins, and I put those systems together, each single configuration of the first system can be matched with each single configuration of the second system, right? So if I have one heads up in this system and all the rest tails, I can keep that same configuration and go through all 2 to the 6 of this configuration, and that'll give me one, you know, set of macro states. And I could do the same thing again with three heads. So that means that whenever we have two systems like the two Einstein solids and we put them together, the multiplicity is multiplied, which means the entropy, you can put them together in that same equation. So if I had these two systems, it ends up being SKLN of the two multiplicities multiplied together, because again, when you have these two systems, you multiply them together to find out the total number of states you can access. Like if this is my A state and this is my B state. So the way logarithms work is when you have a logarithm of something multiplied with each other, that's the same thing as KLN of the first one plus ln of the second one. That's just the property of logarithms. So if you have logarithm of xy, that's the same thing as ln x plus ln y. That's the way that works. That's just the property. And you can put it in your calculator and experiment with numbers. You'll see that's the way it works. So since that's the way it works here as well, even though we're talking about something complicated like entropy. And I could distribute this k and get ln A plus k ln B. And as we can see, we simply end up with the entropy of A plus the entropy of B. So the entropy of a combined system, get my stand here, the entropy of a combined system is simply the entropy, the two entropies added together. I thought that was pretty cool. And this starts to relate to those Einstein solids when we start to put solids together like what was going on in that image. When we start to put these things together and start to calculate the energies of systems that you put together, it can be calculated in this way quite consistently. So pretty cool stuff. And I really like my professor. I mean, he's a really cool guy. He's very knowledgeable. I forget what his specialty is. A lot of times they teach what their specialty is. I forget. I don't know if his specialty is thermodynamics. I don't think it is. But he's really good. And so when I come out this thing, I'll end up having a pretty good understanding of thermodynamics. I definitely have a better understanding of it now. Lisa says I'm getting flashbacks of my discrete math class. I've never taken discrete math. I know we went through some of the concepts in my differential equations class, but I was going to take it when I was going to be a math major. I was going to be a physics and a math major, but I realized that I hate mathy math. I don't want to do proofs. I hate proofs. So that might even be part of the reason why I got a B out of differential equations, because maybe like I wouldn't have been enough. I was thinking about this one homework where I I skipped the proof question, but that's just like one question. So what else we got? What else y'all want to talk about? I see we have a few people viewing. Thanks to everybody who's chatting. Thanks Lisa. Thanks Sean. If you're still there, thanks Shit Heart for popping up. What else y'all want to talk about before I head off? Y'all stay on for another 10 or 20 minutes since I started late. I can imagine. Yeah, I hate mathy math. What's going on, the mathematician? What question do you have? I help if I can. Okay. What question do you have, the mathematician? If I can help, I will. While he's writing this question, I'll see if I can distribute this in a different way here. Put this here. I can increase the size of this just a bit. All right. Try if I can. What's your probability question, the mathematician? You're welcome, Lisa. Thanks for showing up. Thanks for chatting. I appreciate you. Hopefully, I'll see you next week as well. The probability of rolling 3 six-sided die and getting a different number on each die. Let's see about that. Let me put my date on here, by the way. So we at 1524. Get some quantum. Get some thermo. Now we're going to do some probability. All right, so let's see if I can recall this. I'll put 224. Have a habit of doing that. Probably I'll get out of it by like June. By June, I'll start writing 25 by habit. All right, so we have a six-sided die, 3 six-sided die. So 1, 2, 3. I usually start out like this, so I know what I'm working with. Well, I would think that, so the first die, I have 6 different ways I can roll that die, right? I have 3 dice. First time I roll that dice, 1 through 6 is fair game. The second time I roll that dice, I only have 5 ways of rolling it, right? Because the question is, I need to get a different number on each die. So whatever number I have on this die, I don't know what number it is, but whatever number I have on this die, I can't get that same number. So I have 6 options for that die, but I only have 5 for this one. And this one I only have 4. There's 6 options for this one, 5 for this one, and 4 for that one. So I would say 6 times 5 times 4, that is 30. And times 4, that's what, 120? 120. So it seems like there's 120 ways of rolling 3 dice and not getting the same number on each one. And to get the probability, I need to divide by the total number of options. So if I have 3 6-sided die, just like how we did with the coin flip, is going to be 6 times 6 times 6. So I have 6 to the 3 options total. So I would say the probability of 3 die with unique numbers is going to be 120 divided by 6 to the 3. That's what I would say at the moment. So if I was taking an exam right now and I had to solve the problem right now, this would be the answer I would put. I'll put 120 over 6 to the 3. I can figure out what 6 to the 3 is really fast. Let's see what that is. 6 to the 3. So 216. So I would say 120 over 216 is the probability. So if I let the calculator simplify that for me, the probability would be 5 out of 9 that you would have all 3 dice rolling a different number. So that's the way I would do it at the moment. One thing that may interfere is we may need to extract the duplicates. I have to think about if duplicates interferes with this. So, like let's say if I roll, a 1, a 3, and a 5, is that the same thing as rolling a 1, a 5, and a 3? So the question will also have to put into whether duplicates matter. If duplicates don't matter, then it'll be this. If duplicates do matter, then you'd have to divide by 3 factorial. So that'd be 6. So if duplicates matter, then it'll be 5 over 54. So 5 over 54, no duplicates. And 5 over 9, duplicates fine. Right. So from what I recall of my probability class, that'll be the case. What do you think, the mathematician? Does that sound reasonable? How that's done? Okay. Well, I don't remember how to do that one then. So maybe one day I could look up my probability book. What does it say the answer is? I can see if I can figure out what the error is. What's going on, Delta? How you doing? Good to see you. And I did say that right. Right, is Delta? Looks like Delta. Oh, it is the 5-9. Awesome. Right. So I guess they don't mind duplicates then. But if they did not want duplicates, it would be this. But if they don't mind duplicates, then awesome. Well, that's what it is then. The 5-9 with not minding duplicates. Well, there you go. Does that process make sense on how to do it? There's a bit of lag. He might be logging there. And what's on your mind, Delta? Do you have any questions, any comments, anything you wanted to discuss? Anything you wanted to talk about? Certainly. Last question. So we'll do one more question, then I'll close up. I'll come back next week and talk about some relativity. What's the last question you have here? Oh, where did my screen go? Hold up here. Oh, there we go. Guess I can take the book down since we're not talking about uh, thermodynamics anymore. Oh, certainly. So I believe my email. I guess it's not up, is it? Hold on. Let me move this mic so I can type my email down. Send it there. BEBJ@darrellleeberryjr.com. If anybody wants to contact me, that's always a good place to contact me. Good to see you, by the way, Delta. I don't think I've seen you before. Thanks for showing up and thanks for saying hi. Good to see you. What I may do is change up my Earth. See which Earth I like to do at the moment as we close up about this Earth. So changing up the Earth a bit while we're waiting for uh, the mathematician's question there. Isn't that a nice pick right there? And that should be enough time. Let me check my email and see what we have. You want the area of the blue thing in the middle? Oh yeah, that does look like a doozy. All right, so let me draw what he has here. He has a square box, and let's see if I could draw it pretty precisely. And we have this side is 20, and we have basically a curved line going like so, and a curved line going like so. I believe he wants the area inside here. That's quite interesting. So this is how I would do this. So looking at this problem, the first thing I notice is it looks like we're given a radius. So, but this is some assumptions that I'm making here. So it looks to me that this is the radius of a circle, and we know that this is 20 since this is a square. So that's going to be related. Now, if this is the radius of a circle, this suggests to me that this is also 20. this suggests to me that they took a 20 length line and just went like that, 20. So that means we have a radius of a circle that's 20 units. And we have 4 of these circles. So then it ends up being quite simple. So if I have an area that's 20 by 20, so the entire triangle is 20 by 20, equals what? 400, I guess? So that's the area of the whole triangle. And I have to deduct from that a quarter of a circle of radius 20. So the area of a circle is what? Pi r squared? That's the area of a circle. So the area of a quarter of a circle is pi r squared over 4. So that means that the area of this whole thing here is 400 minus pi r squared over 4. Right? So now we cut away all of this. So now all of this is cut away. All of this part here. Looking at it from the other way, I have another circle here on this side. And all we have to do is cut that away. So it's a matter of overlapping these different cuts. You have to think about how that's done. That ends up being complicated. The first cut is pretty easy. The rest is pretty complicated. There may be a way to somehow portion this area. So this area this will be this area here. The area minus all of that is this. So let's see how we might be able to implement that as well. This is interesting. Another thing I noticed, by the way, this area here will be the same area as will be subtracted over there. It'll be the same area. So let's see how we can use this. Oh, and I realized what I did here. I subtracted the wrong part. It'll be this to subtract that. All right, so now we subtracted that. So I would say that minus 400 gives me that. Pi r squared over 4 minus 400 will give me that part. So you have to think about this one more. That'll get you started, though. Yeah, that's pretty interesting. But it's definitely, I would say, to do with the fact that this line is a radius of 20. We need to overlap those full circles. Let's think of something else I might be able to do. Oh, and the mathematician says I don't see how I see the radius. Simply because they wrote a 20 on the side, which suggests to me that the side of that wall is 20. And if you look at this arc is going from a side to a side. You see the arc is coming from this corner and going to that corner, and it's passing in between this corner, right? So it looks to me that this arm here that I'll draw on yellow right now, This looks to me that this is just a fan that I can fan and cover that whole area. So that tells me that this is basically like this. It's hard for me to do it perfectly with the um you know the the scroll tool here, but it looks to me like this. You see that? Like if you was to draw this in the program and do this perfectly, I'm sure you'll be able to see that this line right there is capturing that whole thing. So that means that this radius has to be 20. So now you have a radius. You're welcome. Yeah. You have a radius of 20, and that's a quarter of a circle. That's right. And I'm sure that's what they want you to use, right? So if you take the quarter of a circle and subtract 400, uh, if you take the quarter of a circle and subtract 400, or take 400 and subtract the quarter of a circle, then you get the difference of that area. So it's easier to get one. It starts to get more complicated when we think about how to overlap them. So I'll give it a little bit more thought, see if I can come up with something else. So at this point, all we have is pi over square root over 4 minus 400 is all of this. Right? So you know what? I think this can be solved with integration. This can be solved with integration. And I like integrals too. Maybe I'll take a moment and do this, see what it comes up with. So if I also look at this like this is my y-axis and this is my x-axis, and this is 0 and this is 20, I have lines that are intersecting. So basically I have 4 different lines that are intersecting. I'm going to erase some of this extra stuff. The arc will work, but it's not coming to me quickly. I'm sure there's a way to do it with arcs. But let's say we have uh, one line here, one line here, one line here, and one line there. So basically all we have to do is integrate over that area, and that'll give us the area of that, which means all we have to do is find the parameterization of these lines within those bounds. So for instance, we have a circle. This would be r equals x squared plus y squared. So it's talking about a two-dimensional circle. And in this case, r equals 20. We already determined that the radius is 20. Looking at this, we can say the easy way to parameterize this. So if I was to expand this out, and let's say have this. This will be one circle there. We have a group of circles that's overlapping. What's going on? I would say uh, the circle 1, if I call this circle 1, x equals r cosine theta, y equals r sine theta, and r equals 20. And the origin of this thing is centered at x equals 20. The parameterization, crap, even the parameterization is hard on this. This is actually an interesting problem. Where did you get this problem from, actually? Like, where did you actually get this from? Oh, what textbook is it? I'll put the textbook in. I'm actually have to brush up on my math and stuff over the summer, so that might be interesting in looking at. So basically, if I can remember how to parameterize a line, I remember how to parameterize this line right here. But basically, all we have to do is parameterize the line. It's a what book? Like, what's the title? What's the title of it? So basically, all you have to do is parameterize these lines and take an integral, x, y, and add these things up. Uh, so basically, it'll be uh, x. This will be x1, x2, x3, y1, y2, y3. So you end up having four integrals. You have the integral x1, x2 of the line dx, and then integral x2 to x3 of the line dx. You'd have the same thing for y, y2 dy, y2, y3 dy. And these two integrals will give you the area, but I can't remember how to parameterize the line. This book named The Hardest Math Problems and Puzzles. So aptly named. So aptly named. But I'll think about this one. Yeah. But that's two ways you can do it, though, to get you started. One is to use the fact that this circle has to be a radius of 20, which I was able to show graphically how that works. And the second would be taking an integral over these areas, but the difficult part for me would be remembering how to parameterize a line. So once I remind myself how to parameterize the line and parameterize these lines, and then you can have an equation to plug into here. You can just take the integrals. So basically you have an upper and lower bounds, and the integral over that will give you that area. I was thinking that might be me tonight, but it can't be because I have a lot of homework to do, and I have a paper to write on my research of the perceptive cluster. So, but yes, I did. It definitely won't keep me up all night, even though it's keeping me up a bit now. But I find it interesting. But I'll definitely come back to it. But yeah, it's an interesting problem. But those are the two ways I'll approach it. So, what I may do, the mathematician, is remind myself how to parameterize a line. It's probably the first way I would do. Remind myself how to parameterize a line, and as long as I can parameterize these lines here, then it'll be relatively simple to take some integrals and find the integral of this area. Right now, I'm a learning assistant in a modern physics lab. So it's a laboratory that does experiments like measuring the speed of light or measuring the relativistic effects of an electron, things like that. I'm in school. I'm an undergraduate to be. I'm a double major in physics and astronomy. So I'm a graduating this year, and I should be starting graduate school in the fall for a physics degree with a focus on astronomy. So that's the plan. So I plan on being a physics professor in the future, mostly of astronomy, but physics and astronomy. But awesome. Thanks for the problems, the mathematician. I really appreciate that the mathematician. That'll be greatly helpful for the stats, and it's good seeing you around. So yeah, I love when people join up, have some interesting questions, have some interesting things we can talk about. So if you have some more math problems, bring them. Can't say I'll work on this every day because, like I said, I have a lot of homework and stuff, but I will keep this column in mind. But I do need to remind myself how to parameterize a line anyway. I believe if I could parameterize this line easily, and this is a hard line to parameterize because the circle is way out here, but I believe if I could parameterize this line, it'll be all right. But I'll think about it. You know, we used to seeing circles at the origin. Well, now we have 4 different circles, none of them are at the origin, so it's pretty complicated. uh, is it the hardest problem I saw? I don't know. I don't know if I can say that. The quantum problem I was doing is kind of difficult. I believe I can figure this out. All I have to do is just remind myself how to parameterize a line. Unless the integral will give me some troubles, but I mean, it seems like a pretty simple integral with the parameterization. The quantum problem I had to do over the weekend is pretty hard. I already promised relativity next week, so I would say give me to the first. Look for me on the first. And I believe by then I can have this problem figured out. So on the first, I'll start with this problem and then go with some relativity stuff. Also, my throat getting dry. Should have brought myself some water. I'm gonna head out. I'll be back next week for some relativity. Be back the week after that with the answer to this problem. Thanks everybody for showing up. I'll see y'all next time.